Sharpen up your drawing pencils. We shall now tackle a very interesting and important aspect of coordination chemistry, actually chemistry in general, that of stereochemistry. You'll find out, for those of you who go to organic class, the stereochemical properties of organic molecules are very important. As an example, I suspect you're familiar with termites. They can do a lot of damage because they have the ability not only to eat wood, because we can eat wood, but they thrive on it. They, however, do not thrive on mirror images of wood molecules. We do, because mirror images of wood molecules are sugars. So these rascally termites are not interested in your candy bars. They're not interested in your popsicles. But they like the stick the popsicle is formed on. That they can thrive on. And as we'll see in this conversation, the only difference between the molecules to which I have just referred, because they are structurally identical, compositionally identical, geometrically identical, is that they share the relationship that your right hand shares with your left hand, or left hand with right hand. I'm sure on some occasions you've all shown your right hand to a mirror and see that a left hand is looking back at you, and vice versa. Obviously very similar objects. Thumbs, ring finger, index finger, little finger, all that stuff. Same positions. But if you show this to a mirror, you see this looking back at you, and vice versa. So if you wish to find out if the mirror image of a molecule is something different, because all solid entities or non-transparent entities cast a mirror image. The question is the mirror image different, or is it the same thing? The test that you apply to find out is called superposition. You take your right hand, left hand, put one on the table, doesn't matter which one, you can do this right now, and superimpose the other hand upon it. Lay the other hand upon it with palms down in both cases. And then you see that these parts of the body are different, ever so obviously, because the thumb and little finger positions are reversed. They're not the same. If I want an identical left hand, I have to borrow one of yours. Or identical right hand, I have to borrow your right hand. Now, regarding stereochemistry, again, there are two types of stereochemical species. Two types of isomeric variation for stereochemical species. Geometric, which we've looked at previously. Cis-trans, which leads into facial and meridional, the various platinum complexes, octahedral complex of platinum that we looked at last time. And optical, or mirror image, with the right-hand, left-hand example that I've just offered you. Compositionally, geometric isomers, stereoisomers of each other. Compositionally, isomers, these isomers are identical. Structurally, they're identical. Shape-wise, they're identical. What's different? What's different is the geometric positions occupied by the specific ligands in the first coordination sphere. Again, illustrated by cis-trans complexes of this stuff, which presumably you talked about at least in brief yesterday, because this stuff is square planar. It shows central metal platinum, DsP2 hybridized. Trans, where like ligands are at a 180-degree angle with respect to each other in the square of this complex, versus like ligands being at a 90-degree angle with respect to each other. If you had the wherewithal to make a measurement, what measurement would you make if you had a sample of this and it was this or this? What measurement would you make if you had the ability to make the measurement? Did you make mention of this yesterday? What measurement would you make? In what way are these two molecules different? They're not different shape-wise. They're not different composition-wise. How are they different? Bond angles are all the same. How are they different?
One displays polarity.
How about polarity? Which one of these is polar? You learned about polarity considerations in 2045. Now let's put it to use. Trans or cis? This is polar. Because the platinum-nitrogen bonds have a different bond moment than the platinum-chlorine bonds. But here, the platinum-nitrogen bonds are exactly opposite each other. So the vector sum of these two bonds, the electron density disparity for each of these two bonds, cancels at the geometric center of the complex, which is the metal. Same for the platinum-chlorine bonds. Here, it's rather like, or a way to view this, is the platinum atom is a rock. A big rock in a farmer's field. Farmer wants to move the rock. He's got 2 horses and 2 mules. The horses can pull with the same strength as each other. The mules pull with the same strength as each other. But the horses pull more strongly than the mules. Or vice versa. Maybe they're big mules and little horses. I don't know. Okay? So if the ammonia molecules correspond to the horses, and the chlorine atoms correspond to the mules are pulling this way. The horses are pulling this way. And if these bond polarities exceed these bond polarities, then the rock will move this way, polar. You will not have a uniform balance of these pulling forces upon the rock, polar. Now, more on this optical isomer consideration. Look at this complex. This is a generally octahedral complex of cobalt in the +3 oxidation state, with 3 ethylene diamine ligands in the first coordination sphere. We've already looked on a couple of occasions at ethylene diamine. Just as a reminder, there's an abbreviated Lewis structure for ethylene diamine. But we know that each skeletal atom for this molecule is sp3 hybridized, so it really shows a zigzag shape. Like this. But because of free rotation along these single bonds, this thing can wind up with each of its non-bonding pairs on the nitrogen atoms aiming at the same place in space, and that's what gave me my wonderful Easter bonnet. So, let's imagine that we have cobalt ion in the +3 oxidation state, simultaneously coordinated by 3 of these ethylene diamine chelating ligands. Now, the simplest way to draw a picture of this is start with the canted square, again to remind ourselves that the square is perpendicular to our drawing surface. For a non-chelate complex, these are the atoms in the canted square. This atom and this atom, this coordinated metal, and this atom, the bottom atom, this atom, the top atom, are all in the plane of the drawing surface. They're all in the on the surface of the chalkboard. Okay. Here's a plastic model of this thing. Each of these loops is a simulation of an ethylene diamine chelate ring. Now, I've purposely, in making the model, left out modular representations of nitrogen and CH2 and CH2 and NH2, because then this would be a mess to look at. But here's a nitrogen atom, here's a nitrogen atom, here's a CH2 group, here's a CH2 group. Now, if I take this model and hold it like this, I hope you see the relationship of the model and the picture on the board. Here's this loop right here that's in this square plane of the complex. This loop that's perpendicular to our drawing surface. Here's the top loop right here. The top loop connects the top coordination position to this left rear coordination position in the in-plane square. And the bottom loop connects the bottom coordination position to this left forward position in the in-plane square. So, there's our model. There's our picture of the model. What I've drawn on the board is the mirror image of this. If you take this object, as we had it here, and shine it at a mirror, here's the mirror, what you will see is this, looking back at you. What you will see is this, looking back at you. You see, all this which I'm now holding in my right hand is a model of this sketch, or this sketch is an illustration of this model. Now, this loop is in plane, closest to the mirror surface. This loop connects the top coordination position to the right rear of the in-plane square, right there. And this bottom loop connects the bottom coordination position, right here, to this forward right corner of the in-plane square, right there. So, we recognized that these models are duplicates of the sketches we have on the board, and they are mirror images of each other. The question is, are they the same, or are they different? The test is that of superposition. Since we have the benefit of the models in hand, let's see if we can overlay these models on each other and find out if they are identical or if they are in fact different. So I'll take these two in-plane rings and overlay them on each other. But I see that I have a problem, because the top loops do not overlay with each other. This loop points this way, but this loop points that way. Same for the bottom loops. Here's the two squares looking at each other. Here's the overlay. All right? The bottom loop is pointing that way. This bottom loop is pointing that way. So we see that these objects, which are obviously, I hope to you, mirror images of each other, are also different species, because they are non-superimposable. All right? Now, how can you prove this to yourself when you have to tackle this task on a flat surface, like your piece of examination paper, like what we have on the chalkboard? Here's our sketch. I'm going to imagine to take either of these sketches. It doesn't make any difference. Okay? And hold by the top and bottom coordination positions, which constitutes a straight line, therefore an axis of rotation, passing through the metal atom in the center of the complex. Okay? I'm going to take this picture, and I'm going to rotate it. Okay? 180 degrees. Now, since this loop is aiming right at me, as I hold it like this, if I rotate this thing 180 degrees holding it this way, then this loop is going to wind up aiming that way. There it is. Okay? Now what I want to do is, after I do this rotation, is to draw the picture of this object after I rotated it. Now, I didn't change this. I didn't turn this into something different. All I did was have the wind blow it in space until it spun around and this loop aims that way. But look what happens to the positions of the top and bottom loop. Here again is the model of this optical isomer of this species. Okay? Top loop projected behind the drawing surface, bottom loop projected out in front of the drawing surface, and this loop in this square aiming at me, aiming that way. We rotated 180 degrees. After we rotated 180 degrees, that's what we get. We redraw the picture. This loop is now aiming that way. But look what happened to the top loop. The top loop, since I rotated by this axis, this position of the top loop stays the same. This position of the bottom loop stays the same. But if I take this square, which I told you, if you want to, you can simulate with a piece of paper. Fold it into the shape of a square. Okay? If I rotate this 180 degrees, where does this corner wind up after the 180 degree rotation? It winds up over here. So, if I label these corners A, B, C, D, just for reference, or 1, 2, 3, 4, whatever you want to do. Anything you can do to make this as digestible as you can make it. A comes over here, C goes over there. D goes over there, B goes over there. All right? Now notice B connects the top loop to the in-plane square. So where's B wound up? B wound up over here. There's B, and here's D, and here's A, and here's C. So now the top loop in this spatial orientation is pointing out in front of the drawing surface and in this direction. Whereas previously it was projected behind the drawing surface, but pointing in that direction. Now it's going this way, turned 180 degrees. It went from pointing that way, this loop, to this way, 180 degrees. So we see that A and B, well, small a, small b, my labels for these two original sketches, are clearly different. Let's try what should be a simpler case. And with this simpler case, go back and reconsider geometric aspects of coordination complex isomerism. Question 2460. The formula given in the notes is diaco, diamino, dichloro, cobalt 2. That's the name of this thing. To simplify, let's let A represent water molecules, and B represent ammonia molecules, and C represent chloride ions. So I'll rewrite this as A2, B2, C2. And then I want to look at this note. The note says, if any geometric isomer is optically active, shows a mirror image of itself which is truly different, it will be the one of lowest symmetry. What's that mean? Least symmetric. You know what this word symmetry means? I have a feeling you do. If I stand here and represent a metal atom, and I have a bond projected that way and a bond projected that way, how does my overall symmetry, when the bonds are directed opposite to each other, how does my overall symmetry compare to my symmetry if the bonds are at a 90-degree angle with respect to each other? What if the bonds are at a 45-degree angle with respect to each other? 135-degree angle with respect to each other. Back to the 180-degree angle with respect to each other. 180-degree angle, 135-degree angle, 90-degree angle, 45-degree angle. Which of these angular orientations for the two bonds that I show you corresponds to the least symmetric
45?
geometry? This one. 45. It's like polarity. Any molecule which has an asymmetric, non-symmetric overall distribution of valence electron density with respect to its geometric center is polar. Even the ozone molecule, which is composed of just oxygen atoms, is polar because of its shape. Did you think about that in 2045? Because ozone is an angular molecule. Once you recognize a molecule to be angular in shape, it's got to be at least slightly polar. Has to be. Because an angular species cannot have a perfectly symmetric valence electron density distribution with respect to its geometric center. So, most symmetric will always be that geometry when like atoms are at the greatest possible angle they can be with respect to each other. Now, don't go past 180 degrees, because we're talking about now going to the other side of the circle. In other words, this, which you might call 270 degrees, is really 90 degrees. So, in simulating this complex in this abbreviational fashion, and drawing this, which is the all-trans variant, versus this, which is the all-cis variant, I suspect you immediately recognize that if any geometric isomer for this complex shows a mirror image which is different, is truly optically active. It's got to be this one, because this is the least symmetric. Now, before we move along, I want you to recognize the directive is to sketch all geometric isomers. How many total geometric isomers are shown by this thing? I want to see if I can polish your skills in short order fashion toward learning how to play this game correctly. Well, here's one where all like ligands are opposite each other, the all-trans variation. And here's two, which is the antithesis of sorts of this from a geometric isomer standpoint, because here all like ligands are cis to each other. Well, can I keep the AA's trans and put C over here and B over here? Then I got AA's trans and B cis and C cis. That's another one. Well, let's put the C, keep the C's trans, and put this A over here and this B over here. Then the C's are trans and the A's and B's are cis to each other. Well, let's leave the B's trans to each other. And take this A, and put it over here, and this C and put it over here. Then the A's will be cis to each other like the C's. So, all geometric. 5 total. If you think there are others, the best way to convince yourself that there are not others is to draw pictures. You'll see that no other possibilities exist. It's another example. In fact, this is a wonderful example of you simply are not going to learn this if all you do is watch me do it. You have to do it. You have to play the draw the picture game. All right? So after having recognized that this is the least symmetric, then we can state that if any of these 5 geometric isomers for this complex is optically active, it's got to be this one. Well, let's see if we can find out. Do you agree that this is the mirror image of this? Top atom, middle atom, bottom atom, my axis. Let's look at this complex. Does this look like a model? Let's look at this model. Does it look like a model for this complex?
It's upside down, but yeah.
If you want, I'll relabel this, because the model parts that I have, 2 black ones, 2 green ones, and 2 red ones. All right? So I'll leave the B in here. And do this. 2 greens, 2 blacks, 2 reds. All right? I'll even go back to this. No greens, 2 blacks, 2 reds. Now let's have some fun testing your ability to recognize. 2 greens, 2 blacks, 2 reds, with each pair of like ligands being cis to each other, just like the picture we got on the board.
It's still upside down.
Is this model this isomer? Is it this isomer? Or is it both? Are these identical? Well, before we look further at the model, we've recognized that this is the mirror image of this. So just like I did up there, I'm going to hold my molecule, my model, by the top atom, the bottom atom, and here's my in-plane orientation of 4 ligands, and I'm going to rotate it 180 degrees. That means this is going to wind up aiming this way, and it's aiming this way, and all that sort of stuff. There it is. Okay? I'm going to do it on the board. The top atoms and bottom atoms obviously stay in the same place. They're the axis by which we did the rotation. So, this red goes over there, and this green comes over here, and this blue goes over here, and this red goes over there. Okay? Let's see what we got. We're looking now at this picture and this picture. Green on top, blue on the bottom, blue on the bottom. Red over here, red over here, red over here, red over here. But at this back left corner, I have green, and over here, I have blue. And here, at the forward left corner, I have blue, whereas here at the forward left corner, I have green. So, this thing, pardon me, the all-cis variation of this is optically active. These are the mirror images of each other, and they are different. By playing this draw the picture game and rotation game, we found out they're different. Okay? Which one am I holding? Well, the way we have the pictures drawn on the board, the green one of the green ones is at the top. All right? And the way I have the picture on the board, black one is at the bottom. All right? There's green at the top, black at the bottom. All right? And here's the square. Also, the way I have the pictures drawn on the board, the reds are over here for this picture, but for over here, the reds are over here. There they are. Okay? See the reds? Red, 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 red. Green, green. Black, black. Here I have green. Here I have black. Whereas here I have black, and here I have green. So this model which I'm showing you, which one of these is it? It's this one, isn't it? Well, let's find out by rotating this so as to put the red ones over there. Okay? Red, 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 green, green, black, black, and over on this side, green behind the drawing surface, because here's my drawing surface, and black out in front. Here it is. So this is this. Now, if you were in the laboratory and were really a wizard at synthesis, what would you do to turn this molecule into its mirror image? In order to do that, you'd have to break 2 bonds, no more, and remake the 2 bonds that you broke, while retaining all cis orientation for each pair of like ligands. Now, which two bonds would you like to break and remake? Well, notice if I break this bond and I break this bond, and I put this bond over here to connect the black atom, okay? And I put this bond over here, will I still have all cis geometry? If I break this bond and break this bond. Well, if I put this red atom over here, now I got trans geometry, so that won't work. Well, let's go back to thinking about breaking this bond, okay? But not break this one, let's break this one, okay? Let's break this bond and break this bond. Then I'm going to put the black one over here and the red one down here. Will I still now have all cis geometry? Now keep in mind, we've recognized that the model I hold in my hand is the same as the sketch on the left. Well, let's label these things. We'll take all trans out of the picture, and we'll call this Roman 1, and this is Roman 2. And the model we have is Roman 1. Back to the bond breaking and making game. I'm going to break this bond, and recoordinate the black atom over here and recoordinate the red atom over here. Now comes the hard part, which is why I don't like these models. The sticks are almost impossible to get out of there. Okay? We broke the bonds that we had considered breaking and remade the bonds in the fashion in which we said we were going to remake them, retaining all cis orientation. Now, if what I told you is true, this is now Roman 2. Well, let's find out. Green at the top, black at the bottom. All right? Let's start with that. Green at the top, black at the bottom. All right? And all the reds are on this side. We'll put them over there by rotating. And now, behind the drawing surface, we have green, and here's green. And out in front of the drawing surface, in this in-plane square, we have black, and here's black. So this is now this, and is now the mirror image of this. Interesting. All right? Now, more practice. Because, again, the only way you can get at this stuff successfully is to practice. Another complex with A, B, C. Well, just because we've got blacks and reds and greens, I'll relabel this one like I did over there. Gotta make sure I got enough. We'll make this R3. Let me see what I got. I don't have enough blue ones. A black one. Oh, I got plenty of black ones. Okay. R3B2G. Okay. How many geometric isomers? And if any of these geometric isomers is optically active, which one is it? Does it have more than one optically active geometric isomer? Now, to start to answer this combination of questions which I just hurled at you, I asked this question. Look at this complex compositionally compared to this one we just looked at. Now, it doesn't matter that I've got greens here written first before reds. That doesn't make any difference. If you want, you can put the R's up here in front and the G's over here so it looks like that. Which one of these can show the least degree of symmetry? G2, B2, R2, or, well, let's do what I said. And at least write the ligands in the same order to try to make your thoughts as simple as possible. GBr, GBr, except now it's G, Br, B2, R3. Which of these octahedral complexes will show the least degree of symmetry? Now, we've already recognized that the geometric isomer of least symmetry, of low symmetry for a particular complex, will be that in which like ligands are cis. So let's take this thing and draw a picture. Keeping the like ligand cis. All right? If I put an R up top, what two other coordination positions can the two other R ligands occupy and maintain all cis orientation, mutual, all cis orientation for the three R like ligands?
Any two given corners on the Cantor square that are next to each other.
Say slowly.
Any two given corners on the Cantor square that are next to each other.
All right? Do you recognize I can put the other two R ligands any place except here? Okay? And if I put my second R ligand here, then I have to put my third R ligand here or here, but not here, because then it's trans. Okay? Now notice that as soon as I orient the R ligands like this, by default, the two B ligands have got to be cis to each other. Here, 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 here. Doesn't make any difference. All right? Now, tell me, how many other geometric isomers are there for this complex? The way to find out is to draw pictures. Come on, draw pictures. Is it immediately obvious to you that if you're going to show a geometric variant of this, then we've got to have an isomer where two of the R's are trans? Because if the R's are all cis, then I cannot alter the cis-cis orientation of the B's with respect to each other and G with respect to each of the B's. That's impossible. All right? So I'll put R here and R here and R here. Now, that leaves me with blue, blue, green as a possibility. But notice in this for this geometric isomer. The blues are trans to each other, and the G is cis to each of the blues like it was here. Well, I hope then, if I keep the R's in the same place and put a blue over here, where am I not going to put the green to make something different? Here. Because now this green is trans to blue. Whereas here, G is cis to each of the, not blue, but black, pardon me. All right? So we have on the board sketches for 3 geometric isomers of this complex. Okay? Let's make a model. What did we go with? 3 reds? Okay. Three reds, all cis, which again forces the blacks to be cis and the green to be cis to each of the blacks. Okay? Now, back to the issue of possible isomeric variation by optical activity. If any of these is optically active, which one is it? Well, let's label them. 1, 2, 3. Facial, meridional, trans black, meridional, cis black. Which is the least symmetric? Is it number 1? Because for number 1, we've got all like ligands, where we have more than one kind of that ligand in the first coordination sphere, cis. So if any of these things is optically active, if any of these things shows a mirror image which is different, it's got to be number 1. Is this number 1? This is number 1. All right? Now let's do some more artwork. There's our mirror. There's number 1, redrawn. I hope I'm also showing you, if you practice, you can draw these things just as fast as I can draw them. All right? Red up top, black down below, red, red, green, green, blue, blue, and red, red. Model. We got all the red ones behind, up top, and let's see, we got the green over there, up, there we go. Okay, this, black, 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 red, red, green, green, red, 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 red. Okay? So this is this. Okay? Now I've drawn the mirror image of this. What we want to find out is if this, we want to find out, is this mirror image the same as this? Or is it different? Well, just like we've done before, I'm going to take this thing and rotate 180 degrees. Red, blue, because those are black, pardon me, because those are the ligands along with the central atom that I'm using as a rotational axis. All right? So green came over here, red came over here, black came over here, red came over here. All right? Now, look at this. We'll call this 2 and this 3. But 2 and 3 are the same. The question is 3 the same as 1? Well, let's not call this 3. Let's call it 2 rotated. Red up top, black down below. Red, blue, black, black, red, red, green, green, red. Is this different? Well, it is or it isn't. What do you think? Before we proceed, let's have a vote. How many vote that 1 and 2, which we know are mirror images of each other, how many vote that 1 and 2 are in fact different? How many vote that 1 and 2 are identical? And how many didn't vote? At least we got honest people. Now then, let's take our model. Okay? And see if we can orient the model, which we know is this. We've already proved that the model is this. Okay? Let's orient the model, see if it can be the same as this. Well, we got red up top and black down below. And we got green on this side. But the green's behind. Well, then maybe I don't want this red one up top and this black one down below. Maybe I want this red one up top and this black one down below. All right? So I got red up top, black down below, and red out in front, and red out in front, and red out in front, and red out. Green over here and black over here. How about that? It's the same thing, isn't it? You see the model is the same thing? Now, you may well be saying to yourself, how in the hell am I going to do this on a piece of paper? The question is, really, after I see this to be the mirror image of this, when I only have a piece of paper to wrestle with this problem, how do I want to rotate this thing and then resketch it to prove that this is the same as this? Okay? Well, let's recognize that for what we have, there's only one green ligand. Okay? And the green ligand is trans to red. Okay? That's for sure. Well, here I got green trans to red and green trans to red. But here, the green is over here rather than over here. And the red's over here rather than over there. Let's do this. Okay? Well, I call these 1 and 2. Let's change this to Z and Z. I don't know, something. And we'll call this red 1 and red 2 and red 3 and blue 1 and black 1 and black 2. All right? Now when I drew the picture, this is red 2, and this is red 1, and this is red 3, and this is blue number 1, and this is blue number 2. Okay? Now I rotate it this way, which means this is still red number 2, green, and now red 1 came over here, and red 3 came over here, and this is black number 2, so this is black number 1. Okay? How do I need to rotate this thing to show that it's the same as this thing? Well, for starters, I see that green is trans to red number 1. All right? So I'm going to take this thing and I'm going to rotate it until this green is over here and this red is over here. Okay? I'm going to put it back like that. All right? So now this is the same as this. Well, no, wait, I didn't want to do that. I want to show that this is the same as this. Pardon me. That was a foul up. Let's fix the foul up. I want to show it's this, because we're trying to prove that these two are identical, and this is the thing we're rotating. All right? So over there we got red number 1 over here. So I'm going to rotate this thing by how much? I want to put red number 1 up here so that the green comes here. 90 degrees. Right? Just this much. All right, so taking this, rotate red number 1, and I'm rotating, let's see, this way. Okay, here's my square. Okay, here's red number 1 over here, and here's green. Red number 1 over here, and here's green, and I want it to be like this. I want this green to be, here's the one, okay? I want this to be so that green is over here. I want green over here and red number 1 over there. All right? So I'm going to take this thing and turn it this way 90 degrees. So green goes over here. Zip, that's what I'm doing. Okay, and red number 1 goes over here. And now, let's see. Red number 3 is over here. And black number 1 is over here. And black number 2 is over here. Okay. And that's it. Let's see. Green here. Oops. This is the one I rotated. Got to get these pictures right. My fault. Black 1, green here, red 3. I'm rotating this so that green and red 1 will be here. Red 1 went here, black 1 went here, green went here, red 3 went over there, and this is still black 2 and red 2. Okay, finally got that part right. My foul up. Okay, now we're looking at this. We got red, we got green, we got red, and the problem is here we got red, black, whereas there we got red, black. Okay? So what can we do now to show that this is the same as this? We'll take our model and use the model to duplicate this. Okay? Here we are. Black, black, red, 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 green. Okay? What can we do to show that this is the same as that? Now, we want green to stay where it's at, okay? And red to stay where it's at. So, no matter what we do to this, rotationally, the green's got to stay here. So any rotation we're going to do is on this axis, red through green. All right? Well, let's do this and see what we got. Do we have it now? Green, green, red, red, red up top, red back, black and black. That's it. So, what you want to focus on is the axis that connects the ligand that has no duplicate of itself. Keep that in the same space and rotate until you can then get identical positions shown by the other ligands. Bearing in mind that red 1 and red 2 and red 3 are identical. All we've done is to distinguish between them by labeling. If red 1 and red 2 are in fact different, then this problem grows in complexity, and we'll look at that aspect of this on Monday.
Okay, so if you rotate it any way and you can get the same shape,
Not shape. We're not changing shape.
the same,
We're looking at geometric positions occupied by the ligands.
right, but then is there still possibility of then mirroring across a different axis and then having an optically active isomer?
It depends on the complex.
Okay.
This thing is not optically active.
So even,
That's what I hope we just demonstrated.
even if you put the mirror on a different axis
You can put the mirror any place you want.
and it's still,
Now, you're not going to change this thing by whatever mirror you show it to.
okay,
Okay?
it doesn't matter.
Okay. And again, none of this stuff tonight.